We're given this information for question 13 about a population that is being studied. We can see that each of the generations is 1 year. In part A, we're asked to write down a Leslie matrix for this situation. Our Leslie matrix is made up as follows. Across the top row, we put the birth rates. So that's 0, 1.9, 2.2, 1.2, and 0.9. Then the other rows are made up as follows. Survival rate 1 goes here, and the rest of the row is 0. Then we have 0, then this survival rate, and then zeros, then 0, 0, this survival rate, 0, 0, and finally 0, 0, 0, this survival rate, and 0.
We want to put our Leslie matrix into the calculator. Go to Main, Keyboard, 2D and Calc, and here's the matrix. Ours is 5 by 5, so I'll add some extra rows and then some extra columns, and then it's just a case of typing values in. So 0, 1.9, 2.2, 1.2, and 0.9. I'm going to stop recording while I type the rest of the values in. I now have all of the values in, so what I want to do is store this matrix so I can just use a letter. Press this arrow, go to ABC. Usually we put matrices in as capital letters, although it doesn't matter. I'm going to call it L for Leslie matrix, execute, and now this matrix is stored as L.
In part B, we're asked to find the total female population after 1 year, 2 years, and 5 years. Two matrices that are very useful here. The matrix that I'll call A, which is 1, 1, 1, 1, 1, has 5 ones because this is a 5 by 5 matrix. And a matrix which I'll call B, which shows the initial population. 2, 5, 4, 4, 0. 5 columns because this is 5 by 5. To get the population after 1 year, we do A times L times B. That gives us 31.3, so we'll say that that's 31. For the population after 2 years, do A times L squared times B, and that gives us 29. And for the population after 5 years, do A times L to the 5 times B, which is approximately 76.
I have some other matrices to store. I'm just going to check this to make it into decimal because I think that will be beneficial in the rest of this question. Another matrix that I want to store is the matrix 1, 1, 1, 1, 1. So that's a row matrix, and we need 5 rows. Just put in 1, 1, 1, 1, 1, and we'll store that as A. Then I need the initial population matrix, which I want to be a column matrix. We need 5 rows, and the values here are 2, 5, 4, 4, and 0. And let's store that as B. Now, as an example of the calculations we have to do, we want the population after 5 years. So I'm going to do A times my Leslie matrix to the power 5 times the initial population matrix. Execute, and you can see we get 75.73265, so the population is approximately 76.
In part C, we want to predict when the population will be at least 10 times its original size. The original size, which we can see here, is 15. 15 times 10 is 150. So we're looking for the population to be more than 150. If we do A times L to the power 7 times B, we get 135.60. A times L to the 8 times B is 180.93. So the answer is 8 years. We're now told in part D that the population is affected by a disease and the survival rates have decreased. All of the survival rates are now 0.2. So we need to form a new Leslie matrix, which I'll call L2. The changes to that are that all of these survival rates are now 0.2. We want to know when will the population fall below 100 again. At the end of the 8th year, we worked out the total population before, but if we do L to the power 8 times B, that will give us the makeup of the population, and that's 106.14 and so on, 39.53, 24.47, 8.68, and 2.08. So we'll use this matrix, and I'm going to call it C, as the starting point for the next few calculations.
For the last part of the question, we need to know the population at the end of the 8th year. We don't want the total, we want the actual matrix showing the distribution. So let's do L to the power 8 and times that by our matrix B. That gives us this as the distribution. I want to store this matrix as C, so drag it to here, then go find the arrow, and let's call it C, and execute. It's now stored as C and can be used in subsequent calculations. we also need to change the Leslie matrix. It's probably best just to edit the one we have already. So 0.5 needs to become 0.2. This 0.8 also needs to become 0.2. So does the 0.5, and so does the 0.3. Let's store that in something else. Let's say store it in M. So now to find out the population 1 year after this change, we can do the following. We want the matrix that we've called A, that's the 1, 1, 1, 1 matrix, times that by M, and times that by C. And you can see that we get 177, which is the answer outlined in our solutions.
If I do A times L2 times C, that will give me the total population at the end of the 9th year, 1 year on from the 8th year. That's 177. A times L2 squared times C gives me 100, and A times L2 cubed times C gives me 85. So this is the 10th year, this is the 11th year. So I can now state it's 100 after 10 years, and it's fallen below 100 to 85 after 11 years.